Hi everyone, welcome back. My name is Sam, and today we are building a robot dog. Now, we're not going to be as ambitious as creating Boston Dynamics Spot or MIT's Mini Cheetah, as those each cost multiple thousands of dollars, and my channel doesn't quite bring in that amount of income yet. Instead of those expensive actuators, I plan to use these more budget-friendly metal-geared servos to move the joints. Now, although these are basically just larger versions of a common hobbyist servo, I am going to be using a lot of them, which would easily overwhelm my little Arduino Uno, both in computation and in current draw. So to manage all 12 of these servos simultaneously, I'm using a 16-servo controller called the PCA 9685, which communicates with the Arduino via I2C. And to provide the necessary power, I've repurposed an old computer power supply, complete with a buck converter and custom faceplate, to deliver 5 volts to 18 amps. Later the robot should be entirely battery powered, such as with this little LiPo battery I used for a drone project, which you may see in a future video, but for testing and development, being wired should be fine. At the center of the design is the base plate. This is a flat piece of plastic with a number of holes and 2 pieces sticking out for connecting to the next part, the hip. This is the first set of servos, which is screwed directly to the base plate. They each rotate their entire leg towards the body or away from the body. The next set of servos controls the upper leg. They rotate it forward and backward. The final set of servos are for the lower legs, and they have the most unique controlling mechanism. It's not connected directly to a leg piece, but rather through this long lever arm. Some of you may have noticed at this point why the design is set up this way. All of the servos, aka most of the mass, is located very close to the center of rotation. This is because if we were to have our lower leg servos down by the knee, the upper leg servo would have to work much harder to rotate the same amount, because leverage would be working against us. So to make the system efficient, the most mass is put close to what is rotating it. Some of you may have also noticed that only the front legs were shown in this 3D demonstration. This is because the robot is modular and allows for attaching multiple base plates together to add more legs. In fact, this robot started with only 2 legs before I had enough servos for more. But theoretically, you could have as many as you want and make a sort of never-ending robotic centipede from sci-fi nightmares. Now I need to print and assemble the entire thing. Well, this is neat and all, but I can't use it until I write the Arduino software. I initially used a simple built-in servo control library, but I ran into a lot of issues with them not moving in sync or very smoothly. So instead I found this library called Servo Easing, which uses different methods of interpolating positions so the movement is smoother, and also gets rid of most of the other problems I was encountering, such as jitter and movements not happening at the same time. Another issue I had was that one servo position was not exactly the same as another's for some reason, so I just did some simple calibration by adding or subtracting a constant value from the rotation until they all matched. Now I can upload it and turn it on. I also pre-programmed some poses, which you can switch between through the serial console. Before I continue with this project, there are a few problems I encountered. Overall, the robot was not particularly sturdy, and the amount of flex in between the 3 parts of each leg made it hardly able to stand without its legs splaying apart. So these are the problems and the solutions I used to fix them. This first one is with the hip joint. The screw holes were printed too small, so I used hot glue to fill them in and manually screw. This can be seen on 2 of the older ones, where I did not get the alignment right, and so they have a very slight skewed angle. This can be fixed by just reprinting the part. When I do this, I can also significantly reduce the size of this part, since most of it is empty and unused. The next problem is with the upper leg. You may have noticed that there are pieces of wire or tension string used in the construction of this segment. The one on the end is to keep the 2 sides from pulling apart. Using a more ideal material, this would not be as necessary since it would have closer tolerances and less flexibility, but I didn't foresee this problem. So to fix it, I could extend both sides and add a connector, but that would make it incompatible with the current length of the base plate and increase the overall size. So instead, I will just add a hole with the connecting beam, and oh, well, will you look at that, I already had something similar in the original design, but I figured it would be okay without, for some reason. The next problem was with the end plate that connected both halves together. On some of the legs, the top part is cut away, and this is because it interferes with the lower leg servo's lever arm and would cause collision. On a newer design, there's a triangle cutout, but this is still not quite enough. I also failed to make the screw holes large enough this time, and I suppose this is what happens when you decide to use a limited supply of random screws in a jar. So I would increase the cutout size, screw hole size, and add some more material around the holes to prevent cracking. The next problem is with a servo horn, which I discovered is what that thingy that attaches to the servo end is called. The issue is that it was printed with not really enough space to press fin onto the servo, so it requires a lot of force to do so, and doesn't go far enough to center it, causing this diagonal connection between the arm and leg through the beam. And the final problem is with this beam. I initially 3D printed a plastic pin that would go through the holes on each end, but it would either keep falling out, break, or just be too tight to rotate, so I resorted to just using a piece of bent wire temporarily. And ideally this should be a bolt or a metal pin. So I guess it's time to start printing and assembling. Unfortunately, this was the first time I was trying this blue PLA filament, and it kept curling away from the print bed no matter what settings I had. This would cause this kind of deformation, which was not good for having accurate parts. Luckily though, after many retries I got acceptable results, but they still weren't very high quality. So I resorted to buying a new PEI print bed, and that seemed to work much better than my glass one. I was able to print all of the new parts and assemble them. While this new design does still have some flaws, the second version has become much closer to what I want it to be. And instead of using a bunch of random screws from the jar this time, all of the parts were changed to use M2.5 screws, as well as heat set inserts. This should make the design much easier for you folks to recreate at home, and also not cause any of this expansion and cracking from the holes being too small, or any other problems I had with them. Also, the legs this time are now symmetrical, which is in fact an improvement from the initial design. The robot still slides around quite a bit though, because its feet are just hard plastic. I have seen a lot of people just 3D print TPU feet, but even though I have designed some, I actually don't have any TPU filament to use. Most of those rubber filaments also don't look particularly grippy. And I want the surface to be more like skin than the bottom of a shoe. So I found this silicone self-adhering grip tape that doesn't use any adhesive and only sticks to itself through what I think is a molecular bond, so it is very strong. So I wrapped the feet and now it grips very well to the ground. Another problem I should work on is the hip section of each of the legs. This is because they are only supported on one side by the servo shaft, and this will likely cause wear on the gearing. Ideally, the other side should be supported by a bearing in order to hold the weight, and this would make the system even more rigid. Unfortunately, while I was working on the robot, one of the legs broke. The problem seems to have been with the 3D printed servo horns I designed. The teeth on the gearing are too fine, so it inevitably strips, and then the servo cannot move the legs anymore. To fix this in the future, I can just reprint the parts and make sure they have smaller tolerances. Of course, what fun would a robot dog be if it couldn't move around? So now it's time to implement inverse kinematics. The main goal of inverse kinematics is the ability to input x, y, and z coordinates in 3D space, and having something on the end of many joints, in this case the robot's foot, be able to move there. This process requires calculating the angles necessary for each servo to be at, which is achieved using trigonometry. I won't get too detailed with an explanation on how this is implemented. But if your goals involve making robots, programming, or just wanting to better understand the trigonometry behind inverse kinematics, today's sponsor, Brilliant, is the perfect place to learn how. Brilliant has thousands of interactive lessons in data analytics, math, programming, and AI. Each lesson is packed with hands-on problem solving where you learn by doing, through highly visual and short lessons that put even the most complicated STEM topics within reach. Including stuff I've featured widely on this channel, such as a beginner-friendly course on neural networks and low-level computing, and other topics, all crafted by an award-winning team of teachers, researchers, and professionals. As a person who is mostly self-taught, I know from experience that the most effective way of learning is by doing, not from watching lecture videos. And with Brilliant, not only will you be gaining knowledge in topics you are interested in, but you will also improve your problem-solving skills to apply to any part of your professional life. To try everything Brilliant has to offer for free for a full 30 days, visit brilliant.org/astrosam or click on the link in the description. You'll also get 20% off an annual premium subscription. Thank you to Brilliant for supporting the channel. Now let's see how it performs with all these upgrades. The legs don't appear to have very much wobble at all, other than from play in the servo's gearing. It is also now capable of standing up, which it previously was not. And although I have not programmed a walking cycle yet, it appears to be able to crouch, stand, and lift legs independently, which shows that it should now be very much capable of doing so. Unfortunately, the current state of the robot is not quite living up to my expectations. Because of this, I don't think I'm going to be finalizing it with AI walking and computer vision, but I will use what I learned and possible aspects of this design for a future iteration that is using larger and unfortunately more expensive motors. So look forward to that video where I upgrade this a whole lot. If you enjoyed this video, leave a like, and if you didn't, leave a dislike. If you want to see more like it, I have plans for a lot more, like a drone, robotic hand, and a continuation of my CPU, building it as a printed circuit board. So subscribe to be notified. Thanks for watching.